Welcome back. Brought to you by Forge College, this explainer is where things get real. Look, up until now in our Programming with Solana track, we've been talking about program entry points in a pretty theoretical way. It was a great overview, right? But today, we're putting on our hard hats. We are trading all that abstract theory for concrete code. Let's look at the actual anatomy of a Solana program template.
But before we just start hacking away at the keyboard and writing complex business logic, we've got to ask ourselves a really fundamental question. Where exactly do these functions actually live? Understanding this concrete scaffolding is absolutely crucial. It's literally the foundation of writing secure smart contracts.
Here is our blueprint for this explainer. We'll hit the tiny server analogy, meet the core files, trace a live transaction, and wrap up with key takeaways and next steps.
Okay, Section 1, the tiny server analogy. This is going to be your Web 2 mental model for Web 3. Seriously, if you've ever built a basic web app, you pretty much already know how a Solana program is structured. It's true. If you treat a Solana program template like a tiny single-purpose HTTP server, the whole thing just suddenly clicks. So instead of an HTTP request, your Solana program receives a transaction. Make sense? And instead of a router looking at a URL path, your entry point looks at the instruction data. It then routes that request straight over to the processor, which is where your handlers live. And lastly, instead of database models, we have state. It's the exact same logic flow, just happening in a different environment.
Moving right along to Section 2, let's meet the core files, basically the dedicated workers on your assembly line.
Think of this as your master blueprint. It's a quick summary of the distinct responsibilities for the 4 core files you're going to interact with the most. We've got entrypoint.rs, processor.rs, instruction.rs, and state.rs. Respecting the boundaries between these 4 files is the absolute secret to a clean codebase. So let's break them down one by one. First up on the list is entrypoint.rs. You can really think of the entry point as this minimalist bouncer standing at the door of a super exclusive club. It doesn't overthink things. It just checks IDs, basically ensuring ABI conformance, and then immediately hands off the work. It adapts the runtime signature, catches any top-level errors, and simply points the transaction right on inside. Now, once that bouncer lets you in, you meet processor.rs. Honestly, the processor is essentially the stressed-out middle manager handling the actual business logic. It contains your top-level process function and acts as the main dispatch hub. So it looks at the request and routes it directly to the correct, highly specific handler function to actually get the job done. But hold on a second. How does that middle manager even understand the raw bytes coming in? Well, let's look at the next file to see how this builds. Instruction.rs acts as your translator. It takes all those raw, unreadable incoming bytes and safely decodes them into a really clean, easy-to-read enum variant. It defines what instructions are even possible in your program, and it completely validates the parameters before the processor ever even tries to run them. And finally, we have state.rs. Going right back to our server analogy, this is basically your database schema. It defines exactly how your data must be structured, serialized, and laid out on-chain. So when your processor actually needs to save some data or, say, read a user's balance, it uses the rules and helpers to find right here in this state file. All right, Section 3, tracing a live transaction. We're going to follow an initialize account command right down the line. To really ground this in reality, let's watch a live transaction actually happen. Here's the exact chronological path it takes. Step 1, the entry point shim. Step 2, instruction decoding. Step 3, processor dispatch. And Step 4, state mutation. Let's step through each of these exact milliseconds together.
Okay, Step 1, the on-chain runtime hits the entry point shim. Your entrypoint.rs file receives 3 crucial pieces of data: the program ID, the accounts, and the raw instruction data. True to its bouncer nature, it handles any top-level errors and swiftly delegates the heavy lifting by calling the processor's process function. And then it just gets out of the way.
Next up is Step 2. Because before the processor can do the real work, that payload has to be decoded. This is where instruction.rs steps in as the translator. It'll use a helper function, often something like try from slice, to convert those raw bytes into the initialize account enum. It checks for expected lengths and makes sure the raw data actually forms a valid operation. If it's just garbage data, boom, the transaction is rejected right here. No way it gets further.
Now for Step 3, where our middle manager processor takes over. It runs a match statement on that cleanly decoded instruction to find the correct handler. It sees, okay, it's an initialize account command, and routes it to the specific handler function for that exact command. This is also where it centralizes absolutely crucial cross-cutting security checks, like making sure the user actually signed the transaction and actually owns the accounts.
And finally, step 4. The handler needs to save the new account state. To do that, it consults state.rs to understand the exact binary layout required. It uses the helpers defined there to pack the in-memory Rust structure directly into the on-chain account data slice. If everything succeeds smoothly, it returns an OK right back up the chain, and the transaction is complete.
Section 4, Key Takeaways and Next Steps. Here are the rules for a really clean code base.
Look, understanding this separation of concerns isn't just about making your code look neat. It literally prevents security vulnerabilities. Always remember these core rules, okay? Keep the entry point minimal. Centralize your instruction decoding. Use that web server, router, and handler mental model. Oh, and a bonus tip for sure. Put compile time configurations in lib.rs or build.rs.
This brilliantly illustrates the ultimate boundary you should be maintaining in your code. Read this quote with me. The entry point adapts and delegates. The processor implements behavior. You kind of want to tattoo that on your brain. Keeping this boundary super strict heavily reduces the surface area for subtle access control bugs. So now that we know exactly where the logic lives in the template, we are perfectly set up for our next step. Our next explainer will dive deeply into the key components of an entry point. We'll examine the exact function signatures and the really common defensive checks you need to implement right at that adapter boundary.
But for now, I want to leave you with a provocative question to ponder. What subtle security bugs might hide in your program if you start blurring the lines between your router and your handlers? Think about how a messy HTTP server fails, and then apply that to a financial smart contract. Please head over to forge.college to continue learning and mapping these Web3 concepts to your own projects. I've been your host, and all of us at Forge College cannot wait to see what you build next. Catch you in the next explainer.